Good evening, folks. Today, let us talk about Tokamak energy and faster fusion. And we're going to go ahead and zoom in over here on the side of the article. What is fusion? Fusion is the energy of the stars. Small atomic nuclei join together to make larger ones, which releases energy. All the heavier elements in the universe were made this way. Fusion only happens at very high temperatures, because it is forcing particles together that would usually be far apart. Nuclei are all positively charged particles, so they keep away from each other, just like magnets of the same polarity repel. Nuclei don't want to come together, so the only way for fusion to occur is to heat things up a lot, like in the stars. Why do we care? The world needs a base-load power source that is abundant, safe, and CO2-free. Fusion is one of the few options we have. How could we make the energy of the stars on Earth? First, it involves the heating of our fuel to hotter than the center of the sun, over 100 million degrees. At these temperatures, the electrons of atoms break away from the nuclei to create a soup of very fast-moving electrically charged particles called plasma. Somehow, we have to confine this, or trap it, so that we can keep the fuel hot enough for long enough for fusion to occur. Different methods have been proposed, and the main contenders are inertial or laser fusion, which uses lasers to heat and confine the fuel, or magnetic fusion, which uses magnetic fields. Within the field of magnetic fusion, the Tokamak machine is the most developed and best understood. What is a Tokamak? The word Tokamak is a Russian acronym that stands for toroidal chamber magnetic coils. That is, the tokamak is a toroidal or ring donut-shaped vessel with magnetic coils that make a trap for the plasma. The plasma is heated using microwaves or powerful particle injectors, and it has to be stabilized by carefully controlling the shape of the magnetic fields. When will we be using fusion power? That is the hardest question to answer. Research started in the 1950s, and the big joke is that fusion is 30 years away and always will be. We don't think that is true. We think faster fusion is possible, but it's harder than it was originally thought. Globally, tens of thousands of people are working on it and making progress, but it takes time, money, new materials and technology, and intelligent new minds coming into the field to solve the puzzle of how to create fusion power on Earth. When developing new technologies and expertise, timescales are difficult to predict, but Tokamak Energy aims to demonstrate first electricity from fusion by 2025 and commercially viable fusion power by 2030. Why has it taken so long? Did you know that scientists have actually achieved fusion? Unfortunately, so far they have put more energy into it than they got out. The JET Tokamak in the UK holds the world record for fusion power. In 1997, JET made 16 megawatts, about 65% of what was put in to heat the plasma. Progress towards fusion power was rapid for 30 years, slightly faster than Moore's law for computers. But this has slowed since the JET achievement in 1997. Why? The answer lies in the physics. The fusion power we get out depends on the efficiency of the machine, the strength of the magnetic field, and the size, volume, of the toroidal vessel. Here we can see a nice depiction for us. Progress in fusion has slowed. Wow. Interesting. Okay, so here we go. Back in 1985, when engineers were designing the next Tokamak, after JET, the efficiency of the machines and the magnetic field strength were limited by the technology of the time. Increasing size seemed the only way forward. The world agreed to construct the giant ITER Tokamak in France. Feats of engineering such as this take time. Construction is now well underway, but ITER won't be operating for several years yet, probably be mid to late 2020s. Also, plasma physics is very complicated. Keeping hot plasma trapped requires a good understanding of how it behaves. With all the research over the past decades, physicists are now in a better position to improve the performance of fusion plasmas. Okay, let's move up here. Can we achieve fusion faster? We believe so. In the last few decades, new technologies have emerged, building on all the work that has gone into JET and JET and ITER. It seems feasible that by using a slightly different shaped or spherical tokamak combined with the latest generation of high-temperature superconductors for magnets, we could make smaller, cheaper machines, so make progress faster. What is a spherical tokamak? A spherical tokamak is one that is squashed up so that it looks more like a cored apple than a ring donut. It therefore makes more efficient use of the